All right. So let me get me up there. So Newton's third law. You guys might have your own version of Newton's third law or something. Uh, what does Newton's third law mean to any of you guys? Somebody you could either unmute, or if nobody has a clue, I'll say something eventually. But what does Newton's third law sound like to you?
Uh, I've always heard it as um, every force has an equal and well, no,
Something
every
like,
action has an equal and opposite reaction.
yeah, okay. So let's start with that. That's the classic thing. Action reaction. So let's just say it like that, which means for every action there's an equal and opposite reaction. Excellent. So what is an action? What do you think that means?
Like applying a force.
Okay, a force. So let's pick a force. How about how about I have this book and I have this calculator. Okay? The calculator is sitting on top of the book. So, do you agree that the book is applying a force on the calculator?
Yes.
So, let's say the book causing a force on the calculator is the action. What would be the associated reaction? What do you think? Anybody?
It would be the force of the calculator on the book.
Okay. So, what type of force is the book exerting on the calculator?
Normal force.
Okay. What type of force is the calculator exerting on the book?
Mg.
So now that I'm smiling,
That would be second law, though, wouldn't it? Not third law, because there's a subtle difference in there. I think.
not quite. Let me put it this way. Here is something to remember about this. Just because normal force is down and mg and up, and just because they're equal and just because they're opposite, does not make them an action reaction pair. Everything in there was pretty much true, except for the fact that let me do the picture on the board. This is the most common thing students have a hard time accepting. Okay, it's just not true that N and Mg are action reaction pairs. So let me show you something here. Let's start with that example. Here's my block, and it's sitting here. We know that the floor is going to exert a normal force up. So that's the, let's say this was the normal force of the book on the calculator, okay? Now, there's also the weight. That's mg. Well, another term for that would be what causes this force? What object in the universe causes the calculator to be pulled downwards?
The Earth.
Yeah, so the Earth pulls calculator down with what type of force is that? Gravitational.
Gravitational.
Yeah. Okay. And now here's the deal. The weight force is not on the book. It can't be the action reaction. Going back to this, let me get my book out here in the calculator. So in this case, right, it's not that weight force doesn't exist. The weight force is going down. If there wasn't a planet there wouldn't be a normal force, but it's still not the same thing as the reaction. Okay. The idea is this: the normal force here is on the calculator. What is the reaction? here's the entire planet. There's a normal force. Oh, whoops. I guess, let me rephrase. Here's that book, right? There's a normal force of the calculator on the book. These are an action-reaction pair. Now, I can't draw them right there at the center. Normally, they'd happen right at the same spot, but I just can't, right? So the idea is this is supposed to be the book, and that was the calculator. The normal force of the book on the calculator is paired up with the normal force of the calculator on the book. This is a key to understanding action-reaction pairs. Remember, it's always the same type of force. It always involves the same two objects. This one involves a different object. There's no way that this normal force, which involves a book and a calculator, could be paired up with Earth and the calculator. That's different objects. So action-reaction pairs always use the same two objects and the same type of force, and the direction is switched. And if you could remember that, you will have no trouble with this. Interestingly enough, this may seem like, man, this is just a bunch of words. Who cares? This isn't going to matter. We use this a lot in chapter 6 to understand, wait a minute, I think a force is missing on my diagram, and you go through it and you think about Newton's third law, sometimes you find one. And so sometimes this cool trick of thinking about Newton's third law can actually help us draw correct FBDs and make fewer mistakes and pass this class sooner and start making money so that you can retire sooner. And that's what we really want here. All right. So questions, go ahead.
Yeah. So how come we don't include that normal force on a free body diagram? Oh, it's because it's a free body diagram. Is that why?
Exactly.
Oh, okay. Now that
This
makes
is
sense.
a different body, isn't it?
Yeah. Okay.
Yeah. Now
All
I'm going to
right.
go, pretty extreme here. Check this out. Let's do this is going to seem a little bit comical, but I think it will get the point across. Let's say this is the Earth. And let's say this is a giant box of Swiss cake rolls. No, let's make that Nutter Butters. I used to like Nutter Butters, but you could go with Swiss cake rolls. Imagine how many Swiss cake rolls that would be. Delicious. Okay, so now I'm going to try and draw these forces. Even though I can't quite do it right, I'm going to draw them acting on here. This is just a box. We know there's a normal force up, normal force of Earth on box. Okay. Now there's an equal and opposite force this way. There's a normal force of the box on the Earth. All right. These two are action-reaction pairs. Now, why do we not notice it that much? Well, the Earth is so big, the normal force from this box causes almost no effect on the planet. So, whereas the converse is definitely not true. The Earth, the supporting force helps this from falling through the Earth. That's a big deal for the box. All right. And then in addition to this, at the center of this object, you have mg, and that's the Earth pulls box down using gravity. Well, just like there's a force there, the same force is on the Earth, the same size force, mg, is pulling up. That's the box pulls Earth up using gravity. All right. Now, a point that Esteban alluded to, notice the action-reaction pairs occur on different objects. There's a on the box, on the Earth. On the box, on the Earth. So the blue ones here, that's an action-reaction pair. The normal force between the Earth and the box, up on the box, down on the Earth. There's also mg. That would be the gravitational force acting between the Earth and the box. And then if you think about this, let's do a dramatic example of, say, like the moon and the Earth. The Earth exerts a gravitational force on the moon, and the moon exerts the same size force on the Earth. Now, the moon is more affected because it's much smaller. And so it's not that these forces aren't always occurring in pairs. It's that usually one of the objects is so big, you don't notice the force acting on one of them. That doesn't mean it's not in existence. Let me give you another example. This whiteboard. You can see I could lift this up. So let's say it's maybe like, I don't know, 20, 30 pounds, something like that. I'm pretty big. I'm about 250 here. So when I push on this, you don't really notice me moving backwards at all, right? But what's really happening, if I could exaggerate it, when I push on this, I'm pushed back ever so slightly. Because my mass is more than 10 times greater than this thing, you can't really notice it. But that doesn't mean this thing isn't pushing on me. Just like I push on the whiteboard pushes back on me. All right, questions? All right. Oh, go ahead.
No, I was just going to sound pretty good with that. That was a good
Yeah.
explanation.
Yeah. Let's take a look at a screen share real quick here and see if I forgot anything. Nope, that's something else. Let's go to this one. Whoops. Oh, we don't want to do that one. I think I scrolled down too far. Okay, so here it is. Let's see if there's anything that we forgot. Okay. So you kind of, it's between two objects and it's the same two objects. I just want to point this out. Notice this bullet carefully. Hopefully this makes sense when I say F1 on 2 equals F2 on 1, but F1 on 2 equals negative F2 on 1. If you include the vector symbol up there, we have to include the minus sign because the minus sign accounts for the direction when you have a vector, equal but opposite. So again, if you include those little vector symbols up there, you get equal and opposite. You have the minus sign. If you just talk about the magnitudes are equal. Everybody cool with that, I hope. This is just a couple of sentences, right? When I push on the wall pushes back on me. Now think about this. If you push on a wall, like if you get frustrated with this class and punch the wall, I guarantee you will notice the force that the wall exerts on you because it will hurt. Now, in that case, you're the smaller mass. So we don't really notice the wall moving, but yeah. So it's the same kind of concept there. If a floor, so notice this one. Let's say the floor exerts friction to the left on the mop. Watch how that would be called the action. So let's say this part right here. Sorry, give me just a second. The box in red, hopefully that popped up. Let's call that the action. If that's the action, the reaction is the second half of the sentence. Over here. And if you get used to this, it's really easy to do it. What you do is, notice the objects are the same. You have a mop and you have a floor. Those are the two objects, mop and a floor. Now, the direction changes to the right, to the left. That's pretty easy. And the type of force doesn't change. Friction is still friction. If you get used to this, where the objects and the type of force do not change, only the direction does, these are easy. If you do not get used to that, you will suffer. Something that we were talking about with another student earlier. When students are doing these types of problems, usually for some reason at the beginning, they hone in on the direction and you're looking for a force that's in the opposite direction. That's not the best way to find an action-reaction pair. What you want to do is hone in on the type of force and the objects involved. Then it's easy. But if you try to think about directions, there's many times where there's lots of different forces that are going the right way, and you'd be like, huh, maybe it's this. No, think about the objects and the type of force, and then it writes itself. Okay, let's go back in there. Here's some examples. Here's some stuff to notice. Okay, just some wording. We do not say these first two go together. Objects do not exert forces on forces. You can't say there's a normal force exerted on gravity. That doesn't make sense. Normal force and gravity are both forces. That just doesn't make sense. So what you want to do is you want to talk about gravity is exerted on an object. Or you could say the earth exerts gravity on a book. But you do not say the earth exerts a force on gravity. That makes no sense whatsoever. So watch out. Just remember, objects experience forces. Objects exert forces. Okay. Next, what do we got next here? This is one that kind of Esteban pointed out. Action reaction are always on different objects. And they, I guess, point opposite directions. I've hammered this one all day. They're the same type of force, always. And interestingly enough, look at this cool thing down here. Whoops. This is true if the objects are accelerating, at rest, whatever. It doesn't matter. So what is my recommendation? This is what I've been telling you all day. Write down the objects and the force, and then the direction, throw it in. And then all you have to do is switch the objects, switch the direction, leave the force type the same, you're done. And then notice, this kind of alludes to the point that I tried to deliberately trick you into. Remember, I got Esteban to say normal force and mg were action-reaction pairs. That's the most common mistake. And now that you know, there's no excuse. But I guarantee on your final exam, a third of the class will tell me that normal force and weight are an action-reaction pair. Even though I say, I wish I could slap you in the face with a fish if you say that. But I will not do that because fish face slapping is not allowed. All right. So watch out for normal force and mg. The reason it's a misconception is because they are equal, they are opposite, they just aren't an action-reaction pair. So it's very, very difficult. I could prove this to you in many ways. Look at this. So I argue this might make sense to you because you could understand this. Let's say we have an elevator and there's a box in the elevator. All right. So if I did the free, and let's say this is X, let's say this is Y, and let's say it's accelerating upwards. Hopefully you agree I could draw a free body diagram. There'd be a normal force, mg, and it would be accelerating upwards. So I could write the force equations. It would say N minus mg equals ma, because I'm assuming the normal way is up. Well, when I do this, I just want to point out N does not equal mg. If there's one case where N doesn't equal mg, it's impossible for a normal force to always be the action-reaction pair. And so this is a way maybe that will help you remember it. Like, just because N equals mg when A equals 0, most of the time, N is not even equal to mg. So most of the time, the normal force isn't even equal in magnitude. There's no way it could be an action-reaction pair. What about this case? What if you had a ramp and you put a block on a ramp? Okay, I think you agree there's going to be a normal force this way, mg down, and maybe there's some friction, maybe there's not. Let's just ignore friction. But I just want to point out, sometimes the normal force doesn't even point the opposite way. It cannot be the action-reaction pair. It's not always equal. It's not even always opposite. So if you could get rid of that misconception any way you can, that would be awesome. Any questions about that?
So just to recap, the forces have to be the same force, and it has to involve two objects, and they have to be equal.
Has to be the same type of force. Yes.
Same type of. So a normal force has to be another normal force. Mg has to be another mg,
Mm-hmm.
and they have to
Then-
equal.
And if I
Right, and that-
could I say this? Mg is the size of the force. The type is actually gravitational. So mg's, just think of mg's as gravitational forces. Is that okay?
Yeah.
Yeah, but go ahead. Say again now. Making sure you got it.
So it has to be the same type of force, and
Normal,
it would-
frictional, gravitational.
yeah,
Yep.
yeah, and it has to involve two objects,
Two different objects.
two different objects.
Yeah. So what would be the sentence for this force, and what would be the reaction to that action? What do you think?
So it would be there's a normal force on the ramp, or the ramp on the box, and then there's a normal force on from the box to the ramp.
Yeah. Good. And then the only piece you were missing was the direction. So you could have said up and to the left versus down and to the right, or whichever
Okay.
way it looks on your Zoom channel. Yeah. Excellent. All right. Other questions? All right. So I don't normally do breakout rooms, but what I'm going to do is I'm actually going to do 2 breakout rooms, and I'm just going to pick them manually. And the reason I'm doing that is if you want to learn this particular topic, you've got to talk, and you've got to just screw up these sentences over and over and over again. So what I want to do is I'm going to set you free, and I want you to look at the following questions. I'll put them in the chat here, and you can write it down. So 5.14, 5.17, and then maybe 5.20. These are all on page 89. Okay. And so what I want you to do is I want you to look at those in the breakout rooms for about 20 minutes. I'm just going to split us up in half randomly. Okay. So everybody write down 14, 17, and 20. And then what I'll do is I'm going to stay out of the rooms for a minute and let you start talking just so you can, yeah. Let me do this. And then Memo, you can go in. I'll have you go into breakout room 1. All right. So go ahead and join those rooms and try and just talk. And even if it's not fun, just kind of force yourselves to do it. This particular one, you can't really learn unless you just say it out loud. Okay. Go ahead and join your breakout rooms, and then I'll meet you in there in a minute and kind of go in and out. Okay.